Great. I just want to get a little bit of a recap on the things we have learned today so far. So in the before the lunch, we had a look into the PyPSA framework. Um, uh, you have sort of get a little bit of an idea how a PyPSA model is structured, what the core components of a PyPSA model are, and yeah, you get a little bit of an insight into how PyPSA works, and yeah, Priyesh gave you some insights into how you can analyze and yeah, optimize pipes and networks. Just as a little bit of a recap once again, PyPSA is basically created, pipes and networks are basically being created based on a modular approach. So you have carriers, you have transformers, you have links, you have stores, and you have loads. And in each of these components, they are linked with each others. And basically, what's the big issue about it would be that if you want to really analyze great networks or like whole countries or something like that, if you want to optimize them, it would be very time consuming to create all these single components, every solar panel, every wind turbine, every power plant by your own via the framework. And that's where we are beginning then from the PyPSA-Earth model, because the PyPSA-Earth model allows us to automatically download all the generation data, but also the demand data, and then yeah, doing lots of the stuff we have been doing before the lunch manually, automatically. Yeah, that's where we want to begin with this afternoon session. We will start with a little bit of an introduction why we need PyPSA-Earth. Then I want to show you a little bit about what we can do with it. We will have a little bit of a hands-on session about configuration settings, which you can take in order to modify your PyPSA-Earth models. And then Eddy will tell you a little bit about how PyPSA-Earth works, and a little bit uh, a little bit of an behind the scenes what is going on when you are running PyPSA-Earth. And then you will do some hands-on about SnakeMake with Eddy. You will get an overview over the rules, and then in the end, we will analyze some results and see what we can get with yeah, with our solved networks. Perfect. Let's dive right into it. Why do we need PyPSA-Earth? I guess I don't have to tell much about this. I guess everybody here in the Zoom meeting agrees on the impacts of carbon dioxide emissions on, yeah, the climate of our world, and how further emissions will lead to further warming and further global warming. And because of that, there is a big necessity of yeah, reducing our emissions. And when we want to reduce our emissions, we have to look especially into into the energy industry, because the energy industry is yeah, is uh, is taken to account into around 76% of global CO2 emissions. So what's the solution to sort of yeah, to sort of limit the emissions? Of course, an energy transition, but an energy transition is not only a transition of our power system. Energy is also in various other sectors. It's a transition of heating, a transition of transport, and also a transition of industry. And before lunch, we took especially a look into the power system. What we can do with pipes is also optimizing other sectors. So we can also optimize the heating sector, for example, or the transport sector. We can really analyze the whole energy system, not only the power system only. And if we want to sort of, yeah, limit our carbon dioxide emissions, we have four steps to do. We have to improve the energy which we need. So basically, lower our energy demand. We have to shift our generation into renewable energy. We have to try to electrify our sectors, and for all the sectors which we cannot electrify, we have to find other solutions, like, for example, power to X or biomass. And for all these steps, PyPSA-Earth can help us, because PyPSA-Earth basically downloads all the generation and also all the demand, and trying to optimize the whole energy system, every single sector, to limit to have a cost optimal energy system. And you can sort of, with your configuration, also trying to limit certain constraints, like, for example, carbon dioxide. Now, as we know why we need PyPSA, we want to take a look into what we can do with PyPSA-Earth. And what we can do with PyPSA-Earth is basically modeling a more sustainable future. So in this example, for example, we modeled the whole continent of Africa. On the left side, you can see the energy system as it is right now. As you see in the north, very gas-based, in the South Africa, very coal-based, in between, some hydropower. And then we can optimize this energy system for a certain year. In this case, we just took a look into the power system only, but you could easily also optimize it with various other sectors like heating, etc., etc. And then we get an optimized energy system for a certain year, for the energy system of Africa, for the future. You can then also analyze the current capacity, as we already have seen in the map. The energy system of the continent of Africa is mainly gas-based, also a lot of coal in South Africa. And apart from that, also some renewables with run-of-river and on wind and solar. And what you can also see is the expansion of the generator capacities for the optimized future energy system. So for the energy system on the right-hand side. You can also generate renewable potential time series. So for example, here we have potential maps for wind and solar potentials. You are probably wondering why this looks a little bit different to, for example, the Global Wind Atlas or the Global Solar Atlas. In PyPSA-Earth, we also take into account to land use constraints. So, for example, regions where there are natural protected areas, or where national parks or other regions which should not be considered as potentials are not considered as potentials. But this is also, everything of that is also configurable. So you can say on your own, by adjusting the config file, hey, which kind of areas should be considered as potentials and which should not be considered as potentials. Exactly. Now, as we have seen lots of plots already, I want to just tell you a little bit about how you can do it on your own. So basically, all the plots you have seen the last couple of slides, you can easily do that on your own. We created some tutorials and installation guides where you yeah, get guided step by step how to set it up and how to optimize your energy systems. The only constraint here why we are not doing it during the session is that you need a little bit of an optimization time. So you have to run the model to get results. And because of that, yeah, we suggest you, if you are interested into PyPSA-Earth, to yeah, to get the into the tutorials, set it up, and create your own models and your own results. What we are doing today, we already pre-solved some models, some networks, and we will analyze them together. But before we do this, I want to just wrap this a little bit up. What can we do with PyPSA-Earth? So basically, we can do economic dispatch. We can do linear optimal power flow. We can also do capacity expansion planning. We can look in various sectors. We can, yeah, we can integrate policy constraints into our network. So we can say, hey, we want to have it limited to this certain number of carbon dioxide emissions. And we can also visualize all our our results and our plots. We also did this recently in a study which was recently published, where we took a certain look into the green hydrogen regulation and how it can decrease consumer electricity costs in Morocco. And when we were starting with this scenario, we were starting in the configuration, and that's also the thing I want to now tackle with you together. We will take now a look into the configuration. I will just quickly share my other screen. 1 second. Here we go. I want to do this a little bit interactively. I'm trying to also open the chat right now, and also feel free to always ask questions whenever questions arise, or also answering my questions when I trying to ask interactive questions. So let's go. This is the GitHub repository of PyPSA-Earth. So if you want to get started with PyPSA-Earth, you can clone this and then run it on your machine. When you are starting to set up a scenario, you always do this by modifying the configuration file. And the configuration file is the config.default.yaml. You can, by copying it and name it config.yaml, you can modify it, and then this file is going to be used for your modulations. Exactly. Now, as I want to do this a little bit interactively, I want to ask you, what do you think? What do we need to sort of have the to run the PyPSA-Earth model. Like what does PyPSA-Earth, what needs PyPSA-Earth to optimize the energy system? Especially if you go back into the session before lunch, you had various components. What do we need for it? Feel free to just type it in the chat or okay. So we have already some first answers. One is the location you want to optimize exactly. This you can configure it over this config file. If you go into the countries, you can choose whatever country you want to model, or also, as we have seen before, whole continents. So you just modify here the countries from, for example, Nigeria to, I don't know, whatever country you want to choose, for example, Germany or New Zealand or wherever you want to optimize the energy system. Then we also have costs. Yeah, exactly. We have also some parameters which we can configure here. So one of them is, for example, the retrieve cost data. If this parameter is on true, we automatically downloading the cost data from technology data to have specific cost data for all the technologies we are using. So for example, in this technology data repository, where we are getting the cost data from, is specified how much PV panel costs, what are the CapEx costs of it, what are the OpEx costs of it, and also for every other technology. So for onshore wind, for all the fossils, but also for all the storages and all the transmission lines. So for every technology that we are using within our modulations, the costs behind that is retrieved when we are activating this config parameter. We recommend always to set all at least the 4 parameters here to true in your first run. After you have finished your first run, you can set them to false because then you have already downloaded all the cost data and all the additional other data and can save a little bit of computational time when you are deactivating it. But for the first run, always set that to true because then you're getting the cost data that you need to optimize the energy system. Then we have also the demand and the input data like generators. Exactly. That's also something which we are configuring via this parameter, download OSM data. If this one is set to true, we are downloading the data from OSM, which is, for example, all the transmission lines, all the generators and stuff like that. And based on that, we trying to build up the energy system as it is right now. Then we have also a comment which was demand. That's also something which we are downloading and calculating. So basically, we are not only downloading the current demand, we also downloading various other data sets. We trying to estimate future demand projections based on some UN data sets where we basically trying to project the demand and based on that, having future demand, which we are trying to match with our optimization of our energy system. So this is also being done with these 2 enablers. yeah, that if they are set it to true, we are downloading lots of data, which we are using to calculate the demand. And another thing about the demand, we can also um, uh, trying to configure which, if we are rather optimistic or pessimistic in our demand projections. So we have within this scenario part, we have a part which is named demand, which is right now AB. This stands for ambitious. So we are thinking the demand projections will be ambitious. You can also set them to various other settings. I will just quickly show you some of them. So basically, when we are taking AB, for example, for the demand, in all these config parameters, the model is using the ambitious settings. There are also other settings. If we, for example, would have used BU, it would be something like business as usual. Then our scenario would be a business as usual scenario. And as you can see within the config, then you see certain values for different demand projections for different different demands of different sectors. So this would be, for example, demands for land transport fuel cell share in an ambitious scenario for 2030. 1% of the land transport would be powered by fuel cell. We also have that, for example, for the electric share, there would be for 2050 in a net zero scenario, it would be 68% of the land transport would be electric. Exactly. So that's other things that we need. So we need demand. Then someone mentioned renewable profiles. Exactly. We also need renewable profiles. And I already mentioned that you can sort of configure which kind of land areas will be considered as potentials. You can also configure that via the config. So basically here we could in the on-wind session, we can configure which kind of areas are potential areas for onshore wind. And there are various grid codes which are listed here. And depending on the grid codes which we are then configuring here, we have potentials in, for example, urban areas or not. And you can also, especially for wind, this is really useful. You can also configure distances. So for example, you can configure that around urban areas, there has to be a distance of 1,000 meters where no onshore wind is allowed, for example, or something like that. So this is also all configurable throughout the config. And that's not only for wind, also for solar, and so on and so on. So that's about the renewable profiles. Then another comment was the time frame. That's also a good thing. You can configure for which sort of year you want to optimize your energy system. So, for example, here with the planning horizons, we would optimize our energy system for the year 2030. Exactly. Yeah, that's all the guesses from the chat. that was just to give you a little bit of an overview about the config. Yeah, it is in the beginning a little bit overwhelming, not only in the beginning, maybe also later on. But you can really start very basic and very simple by just, for example, editing your country, and all the other config parameters are in the default config somehow adjusted how most of the people want to sort of model their modulations. So yeah, don't fear it. Just try and get started. Just type the country you want to model, maybe your home country or something. Um, Look at the energy system as it is right now, and also then into the results, how it will be extended in the future um, for your yeah, for your country of a choice. Um, exactly. I just quickly scan a little bit through the questions if there are some open ones. There is a question, is it available for all countries and island states? So basically there has been modulations for every UN country, at least for the power system only version of PyPSA-Earth. So it's available all around the globe. So no worries, you can basically model everything. Um, uh, exactly. Then I just want to quickly go over another two or three most important config parameters which haven't been mentioned yet. So one config parameter which is very important is the clusters. With the clusters, you can basically scale the spatial resolution of of your um, your model. So, for example, if you want to model, I don't know, Germany or something, um, uh, Germany would be modeled in this case then by splitting it into 10 parts. So the higher the number is that you are adjusting here, the yeah, more spatial resolution your results have. So the higher resoluted your results are. The big downside behind just adjusting it to any high number that is in your mind is that then the computational effort is being increased. So in general, clusters means basically how many regions, like in how many regions the country of your choice or the region of your choice will be splitted. Many people, for example, just are just taking the numbers of the JADM regions of the country. That's all. That's kind of a good suggestion, but basically you can adjust it however you want. Um, just be aware the higher the numbers, the longer your modulations will probably take. Then another really important config parameter is opts. Basically, with opts, you are setting on the one hand the CO2 limit. So if you are setting your opts to, for example, CO2L 0.05, that would mean that you want to optimize the energy system, the current energy system for the future, for this planning horizon, based on and there is not allowed to be more than 5% of the current emissions you have in the energy system. So with this parameter, you can easily adjust how many CO2 emissions are within the energy system in the future. Then there is another thing behind it, which is in this case 3 hour. This would be the time resolution of the model. So in this case, If you want to, if you want to model the power system of a certain countries with 3 hours, you would have a 3 hourly resolution. So basically, every 3 hours, the supply has to match the demand. Um, you can also adjust this number. The lower you adjust this number. So, for example, if you want to do it in a, I don't know, 1 hourly resolution, every hour the supply has to match the demand. And basically, we are calculating every single hour of the year. So the lower the number is, the more computational effort is behind solving the model. We also have this for sectors. So basically, S-opt means on which time resolution we are solving the network for the sector couple version of it. In this case, it would be 144 hours. That would be very purely resoluted. So I would suggest to do it at least 6 hours or something like that if you have the computational power for it, because then you also have day-night cycles in it and stuff like that. And yeah, then your results will get better and better. Exactly. Um, for all of the people who are interested into hydrogen, for example, and into hydrogen exports, we also have a parameter to export hydrogen. So, for example, if you want to make a case study to decarbonize the energy system of a country of your choice, and at the same time exporting hydrogen or something like that, you can also add this via this config parameter. Yeah, so that's a little bit of an overview over the config and what you can do to sort of build your own scenario. And now I just want to quickly answer some questions about it, and then Eddy will take over and will show you a little bit about what is going on in the background when you are optimizing your scenario, what is going to happen, and then how you can analyze your results. So, are there any questions open yet? I see many of them are already being answered from Eddy. Thank you very much for that. Are there any other questions yet? Okay, then Eddy, the floor is yours.
Yes, thank you, Anton, and hello, everyone. I will share my screen also in a second. Mhm. Sorry for that. Okay, do you see my screen?
Yep.
Okay, awesome. All right, so yeah, I will take over now just to dive slightly into how PyPSA-Earth work in the background somehow. and then dive also into the most important tool within PyPSA that makes everything even possible to have a workflow is actually the snake make. Today morning in the session, we also touched upon this and explained it slightly, but I will dive into this more deeper, and then we can also just work on this directly hands-on and then see exactly how it is on the concept of it. Because understanding this is actually basics to understand, okay, how the model works and how I can actually also adjust stuff and to just understand also the interactions. Because when we say automated workflow, it means we just give one command and then everything's being done at once. From collecting data to downloading them to filtering them. As we can see here, data fusion modification, and then also setting up the PyPSA network, and then adding all the sector coupled components and then solving it. So yeah, so the PyPSA-Earth itself is a sector coupled open model, of course, and then as I said, it's purely automated workflow. Definitely the user, in addition to the config file, if the user already sets the config file by itself without any custom data, then the model can run and then give already some results. Um, Definitely, I've seen also already some questions in the chat that okay, if we have poor data for some country or something like this, we already provide custom data at many levels, where the user can actually define, let's say, the regions of each node and so on, or let's say their own power plants or their own industry data set and so on. As we can see here, that the largest part of the model, of course, is actually collecting those data and then fusing them together and then making sense out of this data so they can feed them directly to and build up the model itself. So it's very uh, data automation is a key, and then this is where SnakeMake comes into play. So I will just before diving into SnakeMake, I just want to show exactly like how a node is represented within PyPSA-Earth. So as we said, this is already sector coupled, so it's not only the electricity in the middle, but we also have oil, we have biomass, we have heat, hydrogen, natural gas, and also CO2 as an energy carrier. And for hydrogen, for example, we also have interaction between the nodes as hydrogen pipeline. For natural gas, the same. For biomass, we even allow also transport of biomass between the nodes. And here, when I say nodes, are the regions within a country, or depending on how many nodes the user sets it up, or according to the clustering itself. And we can also see here the interactions between those carriers. For example, let's say we use electricity to produce hydrogen by actually, I can just do it here. Yeah, exactly. So we use electrolysis, for example, to produce hydrogen, and then the signs here, the minus is the withdrawal, and the plus is the supply. So we can just use hydrogen for fuel cells, for industry, for navigation, or for export, for example. We can also, for example, if it's activated or not, depending on the user, definitely, and the config file, but we can use, for example, Sabatier to just actually also use hydrogen to produce natural gas, if necessary in the future, maybe 2050 on long runs. We can also use steam methane reforming with CC and without. Yeah, also we can use the fuel cell to generate again electricity. All of these, if activated by the user, then the model will optimize according mainly to least cost at the end. Yeah, so this is purely just a small overview of how each node has all of these together on top of each other. Of course, for some node, for example, if there's no biomass potential there, we just don't, is not being used and so on. So this is, as I said, a lot of them are geospatially resolved. Then the demand sectors we have residential demand sector, we have industry, land transport, aviation, shipping, services, and agriculture. Now, I will dive slightly into the idea of SnakeMake. SnakeMake is actually it originally comes from the bioinformatics field, and then the best word for it I can always say it's the orchestrator of the whole workflow. So it actually the user does not have to do anything, and then um, the SnakeMake itself will orchestrate everything. And so because there are many reasons why we need to have this. Already, Anton already mentioned a lot of them. I will mention again here some. We will change data sources, some custom, some not. Many data sources also need a lot of cleaning and processing, and we don't want to do this by hand every time we do a new scenario or we change anything within the model. There are many intermediate steps to be done by collecting some data, by filtering them, by converting some them, and so on. We also have a lot of packages and softwares dependencies, as we saw also already today morning, and also these needs some care. And this is why everything is automated and the environment is set up at once. Yeah, and then also the user can change already some data, can change some code because everything is open source, and accordingly, the user only changes part of the code and then do the full run again and see if everything's working. And that's why we make sure every time that someone changes anything within the code, that the full workflow is still working. And that's why whenever we see anything on the GitHub, so it's most probably everything is working already there and was already tested as a full workflow. And we want to be able to reproduce the results. And this is very important because it's a key thing nowadays, especially in the scientific world, to have reproducible results. And it's not like everything is in a black box and so on. So this is actually the power of PyPSA-Earth and PyPSA itself, that is actually open source and reproducible from everything, from data to the scripts and the workflow then itself, and then to the results. So transparency here is key. And of course, we want to run multiple scenarios at the same time. And this is, we will see now, SnakeMake provide this easily by just changing one part of the config, and then snakefile or SnakeMake detects this and then does the run again accordingly. Or we can have wildcards. This is something that Anton did not touch upon within the config file, but we can see that there are some wildcards, and this accordingly for example, let's say demand year, or let's say anything else. I will show you also slightly the wildcards, and with this, the SnakeMake reads those wildcards and accordingly automates in parallel, if necessary, those scripts or those runs. Here is a small miniature example of a SnakeMake. This is just very easy thing to just actually understand what is SnakeMake and what does it do. So it's in simple words, the user can define in the snake file, define rules, and this rule does execute a task. And this, for example, could be a script that was written in Python. And with this script, there is an input and output for each script. And if there is another rule written in the snake file that has an input that was actually produced by another rule earlier, the user only has to set up these input output, and then the SnakeMake will detect this and run this accordingly. So that's the beauty of SnakeMake, that it automates all of these. Just the user every time does not, like itself, does not have to revisit the snake file every time, of course, unless you are building a new feature, you're adding a totally new script. But then this is done at once, and then the model will always detect these interconnections, and then will execute it accordingly. So a command that might, let's say, run, or it can run the SnakeMake. For example, here, if we run SnakeMake figures, great stuff.pdf, let's say, it means this is the output of rule myplot. And accordingly, the model will know, let's say SnakeMake will know that we'll have to run rule my task first, and then afterwards rule my plot. I guess it's an easy concept. We will dive into this slightly in a bit. So this is a snake, very simplified snake make workflow within PyPSA-Earth, where we just get first to download all the data necessary as input, like raw data, then process this data, and then afterwards build the electricity system model using PyPSA, simplify the electricity system model, let's say also by clustering and so on. And then we extend the model by other sectors and the sector coupled part, and then we solve and summarize and of course visualize the results. All of these can be at the end orchestrated within multiple scripts and with SnakeMake itself. So every time we need to run multiple scenarios, let's say we just change slightly the config files and then run it again, and then we get everything already solved. Now let's move slightly to a SnakeMake workflow within PyPSA-Earth. This might look now a bit overwhelming, but it's not that much because you don't have to worry as a user with all those interconnections. That's what SnakeMake does. And then now we will see this slightly in a bit when we go hands-on and just play around a bit with SnakeMake. So in order to do this, I will share actually the link here, or Anton, if you can actually share this in the chat. So this is directly the link to the notebook. You can just download it and then put it on your Google Drive, and then from there just double click on it, and then you just run it, and it's actually a Google Colab, of course. You cannot run it right away as it is because I guess it's only readable from my side. So you just have to download and put it on your Google Drive and then run it accordingly. I will also do the same. First of all, are there any questions already? I was not able to check the... All right, everybody was able to connect and download it? Okay, Anton, if there are any questions in the chat, please help in that. All right. I guess I can actually start with this. So here also very similar to the first session we had today in the morning, we can see the contents of this notebook. And on the left here, we can also click and see the data that will be now downloaded soon if you run this. Yeah, so this is actually the notebook that will dive with it, the SnakeMake, and some actually maybe dive into one rule. Let's see now according to time. So first of all, we need to run and install the required packages as usual. We can here just even if we double click here, we can definitely see also what kind of packages are we installing. That's now the cool thing about Google Colab, that you don't have to install this on your computer, but just install it here to run the model. Then we have to import also the necessary packages. Here, if I can just also show you. So these are the packages that we want to import here. Already done. Now let's download the needed data for this notebook. If we double click also, we can see how this is being done. So we download them from my GitHub, Google. These data actually are not from my, no, so not from my drive. They are just from another drive. And what we need to do here is we need to just change now already the directory, because I downloaded these, as you can see here. I'll just click again in minimal example. So these files are now available here. And because I'm on the upper folder, I need to just go to minimal example. And then here with os.getCwd, we can check exactly where are we now. So now we are in content, which is actually this folder, the higher folder. And then we are in minimal example. And then now we have already a snake file here. I can also show you the snake file. If you double click on it, you can see already the snake file. There are rules, as we've seen before, of course, slightly more rules. So once we talk about snake file, there are also some dependencies between the rules, and this is actually determined automatically, as I said. And this creates something called DAG, which is directed acrylic graph of jobs together. Now we have we can actually check those graphs. I will just close this again before. So how does the snake file looks like? Either you run it this way or just double click on it, and then you see already that we have rule all, we have rule retrieve data, we have rule build data, rule prepare prepare network, and then the last rule is rule plot benchmark. And you can actually check out the scripts here. So for this, let's scroll up a bit. For example, for rule prepare network, it uses the script called prepare network.python, which is inside scripts. So this snake file that is outside knows that he has to go to scripts and then use prepare network for this rule. For that, he has an input file, which is data filtered.csv. This again is here, data filtered. So the input is already there. The same goes for rule build data. And the output is data filtered, but the input is raw, and it uses build data as scripts. So this is build data again, and data raw is here, and so on. So we can see if we want to, let's say now run, only snake call, and then we say data benchmark.pdf, which is the latest, or let's say the last rule. And here, if you can see, this is already in between brackets, and this means that this is a wildcard. And the wildcard is here is called extension, so we can have a PNG or a PDF plots. And this is a wildcard, and then this is how SnakeMake uses this as a wildcard and produce at the same time both outputs. So it will produce PDF and it will produce PNG for this rule itself. So now if we trigger this one, we will produce only a PDF because we said SnakeMake call this already the output. So we can call output or we can call a function itself or the rule itself. So by calling the output and saying PDF, it will only produce for me PDF. You cannot actually call a rule that includes a wildcard without specifying what the wildcard should be filled with, because this way SnakeMake will not understand what to fill it with and cannot run it. If that's for this, we can run here already now. Let's try plot benchmark, and the model will give us this error. So you have to specify, as we did here, we need to specify exactly the output. For example, for prepare network, if you just run, for example, SnakeMake call prepare network, it will run it totally because there's no wildcard there. Now, you can also have, we have a common rule here, which is all, which can be used to execute the entire workflow. So it takes the final workflow output as its input and thus requires all the previous dependencies rules to be run as well. So once we just run SnakeMake call all, which is, if we scroll up again, so this is the first rule written in the snake file. If you call this one, it already gives it that it needs to produce the PDF and the PNG of the rule plot benchmark. This means it has to run everything. At the same time, because it is also the first rule, we can also just call snakemake.call. And then this way, SnakeMake always uses the first rule. So placing the rule is only important if you really want to just call it first or not. Otherwise, these rules can be just placed anywhere within the snake file. Most importantly, as that the inputs and outputs are all matching together. And then the SnakeMake will actually make the connection between them. Any questions till now? All right. I will just go further. So now there's also an option to just check if all the rules are working fine, which is actually by flagging with -n, which is called a dry run. This way, the SnakeMake will do a dry run, will not really execute everything, will just check if all rules are connected to each other and if there is any problem. And this way, let's just try now the SnakeMake call, which is actually runs everything, and then put a -n, which is the dry run. And if I do it here, also you can do it on your screen, we see that it runs, or it shows us that it will run those all plot benchmark, and then accordingly the run is successful or will be successful. Now let's visualize what is the DAG. So what will the model actually, what kind of rules will be called one after the other? And here the DAG actually also shows us if there are any wildcards, it will show right away already that in the plot. So we can see that plot benchmark is shown once for PDF and once for PNG. And this will show us or tell us about all the wildcards. Here it's also important to see that some of those cells are dashed, whereas the others not. And this means that I ran before the plot benchmark PDF, and these were already ran, and we have results. So if I just now run the all, so those two remaining will be run accordingly, and then the model will finish. Alternatively, there is something called rules. Let's say, sorry, rule graph. So this will only let's say, just plot or show us the interaction between all the rules without saying or without taking into consideration the wildcards. And this is very simple or simpler than the DAG graph, mainly for visualization and mainly for complex models to just see, okay, what are the rules that will be run if I just do or give this command? Here I will also, you can also run this on from your side, and then you can see that the rules here are without the plot benchmark, which is without the wildcards. And here it doesn't say, okay, which one was already run or not. It just shows us what are the rules that will be run. Accordingly, we can also have something more to understand more, okay, what are the input and output for each rule? And if you want to visualize it and not go to the snake file, we can also do this by just plotting the file graph. And the file graph, as I told you before, is actually giving all the rules in addition to their input and output. And this way we can understand how SnakeMake will actually perform the workflow and with which input and which output. This is, of course, a very simple small SnakeMake workflow. Now, if you already understood this and if you don't have any questions, we can move to some kind of small exercise for you where we can perform those small tasks from A to E. I already left some slots here for you. You can run those tasks and I give you around maybe 10 minutes. So I saw some people were asking, okay, how do we start with this? So what do we want to do here? As in task A, we just want to have execute a dry run, which is with the -n, to produce the intermediate file data base 2030 NC. And this means we can just say to snakemake, call this output, and then with -n. So here it tells me that everything is already done, and there's no need to run it because it was already run. As we already seen here on the top part, that all of these are already done. So now I won't say more because I guess I will give some time for others to go further. All right. Okay, I hope it wasn't really difficult. I hope so. So for the second question, execute the entire workflow and investigate what happens if you try to execute the workflow again. So let's execute the full workflow by just calling snakemake call, or we even just call the last um, either PDF or PNG. So for example, now it ran and it was done. If I just try to run it again, it will just give again that everything is already done. We don't need to run anything again. So SnakeMake already knows and remembers if the jobs were done and if you have already output for each rule, and then the missing output, he knows that they are missing still, and then it will run until all the rules, or let's say the target command or call is satisfied. Now for C, let's try to delete the final output, which is benchmark PDF, and investigate what happens if you try to execute the workflow again. So we just go here again, which is, yeah, that's it. So I just say, okay, I want to delete it. Fine. So now SnakeMake should detect this. And if we run it again, it should rerun at least, of course, not at least, but it will run the last one, which is plot benchmark. So it detects that already the output is not there, and accordingly, it runs this in order to satisfy the command. Now, if I just run it again, it will give me that everything is already satisfied, and there's no rule. That's it. Nothing to be done. So with with D, change the value in the raw input data file and save it again. Overwriting the original file, investigate what happens if you try to execute the workflow again. So it's better here with this hint, in order not to change, we just tell or trick SnakeMake by telling him, okay, we already changed something there in this file. That's what .touch means. And then if we run it, the SnakeMake will know that we already changed something there. And accordingly, it will run again the related rule and everything afterwards. So I just maybe also delete it here and run it again. I deleted. Okay. So now for E, we want to open the snake file and add a second rule that processes the file. It's called data row 2, using the same script as the build data rule, and add the output to the new rule as a second input to the prepare network rule. And this means if you just click on this snake file, so we want to add additional rules that have a different input and a different output. So if we add here rule retrieve data 2, and then we just say, okay, we take the data row, we just copy it here. This shell copy input output means that copy it here, put it there, and then the rule build data 2, which just takes this output as input, gets it filtered, and afterwards take those two input, both filtered, and then generate, let's say, an output which is called base 2030. So this is if the user wants to add new rules, new scripts to the model, this is how it can be done. All right, any questions? Anton, I'm not sure.
No questions open, I guess.
All right. Okay, so let's go with let's see actually what are the rules and the workflow within PyPSA-Earth. Here, because PyPSA-Earth has a lot of rules, and we have to have all the scripts and all the data related to it, the input and output and so on. I won't be doing it here, but at least we can actually also visualize and see the rule graphs that I already did before. So it's something similar. For the electricity only, we have two actually ways of optimizing or solving the model. We can solve the model purely on electricity side, or we just do the sector coupled model. So on the electricity side, we just have the snake make call. We say, okay, this is the configuration file, use it, and then I say the rule, which is actually here in this direction, we use solve all networks. We will dive into this later. This actually solves the network only as electricity. And then we tell him to use the script to do it, and then of course output it as PNG. And accordingly, we get this as the electricity only workflow, or let's say DAG of jobs. The same can be done for sector coupled, which actually just calling another rule, which is called solve sector networks. And this way we solve the sector coupled network. And we can see that a lot of other rules are called in addition to the electricity network. So here, this is the last part before solving, prepare network. And then in addition, we add a lot of other rules in order to just further go to solve sector network. Now, if you want to visualize the file graph also for the sector coupled network, or let's say only the electricity network, here we can see all the input data. So if we retrieve the data bundle, here we will see all of this later also on the slides. We see all the cutouts, the Copernicus, EEZ, all those data that are downloaded. From that, we build shapes. And afterwards, we also download the OSM data. We clean those data. We build the OSM network. Afterwards, we do the base network itself. From that, we also build the power plants. We build the bus regions. And then we also do the demand profiles, renewable profiles, and this cost data. This is what also Anton was talking about, that we actually also fetch this online. If the user does not put this as in the config file as true, then whatever is placed in this location, let's say of the input file, it can be custom, let's say here, that you change your own cost accordingly, and then you put in the config false, but still the model will read this without fetching it. And that's how you can actually set up your own costs. Yeah, and then we'll see all of this again step by step in a bit. So we'll have the add electricity. This is where we build up the electricity network. Then we simplify it in order to be solved. And then we do some clustering here. The clustering, we will see it also later. It depends either as Anton showed, which is actually according to demand or generation. But also we can do it according to setup region by the user itself, or according to GADM administrative regions. Yeah, and from that moment, we just go to add some few extra components here. Let's say some storages or some hydrogen pipeline and so on for the electricity network itself. And then we just prepare the network and then solve it. And then the whole thing is already optimized. For the sector coupled, a lot of other rules are added. I also won't show it in here for the time being. Before, maybe you can come back to this. There is one rule here I wanted to show you guys how it works. It's called prepare energy totals, and this is where we prepare the energy demand, the current energy demand for the country itself from the UNSD, United Nations Statistics Department. We download the data from there. and accordingly, and then of course we filter them and so on. But within the prepared energy totals, we just get the base energy totals that are from the UNSD, which are the current ones, and then we extrapolate them, or let's say estimate the future demands per sector and then per carrier, let's say, in the future. And this, a lot of all of these parameters are set up by the user. So how much um, um, how much energy efficiency for each sector will be in the future, or growth rate, and so on. But I guess if we have time later, we can dive into this. I will come back to it later and show you this in order not to complicate the stuff for you. If you have any questions already at this point, I will just go back to the chat if Anton did not answer everything. All right, okay, I guess we're good. Nice. Then we can just go back slightly now to our slides. All right. So now the workflow that we saw now already in the snake make, how it was actually shown as a graphical way, we'll just slightly dive into this now step by step and see what happens within the model in the background. So this rule retrieve data bundle, which is at the beginning. So it simply downloads the main data, raw data that we need. It is actually, for example, let's say the EZ shapes that we saw there already in the input. It's like the exclusive economic zones shapes. So it's actually be used for identifying the marine regions for each country and accordingly estimate, let's say, offshore renewable energy potentials. Um, we also have the Copernicus land cover, which updates, which gives the update on the Earth's surface coverage. For example, let's say including forests, grasslands, croplands, lakes, and wetlands, and so on. All of these can be or will be used actually at the later stage to just have exclusion criteria for the potentials of renewables, for example. We also have the hydro basins, which is actually the watershed boundaries and the basins also on a global scale. The model will definitely does not like we will use according to the geographical location. We'll collect these and accordingly calculate the the hydro in feed. We also have, we also need to get also the historic hydrogen generation and accordingly fix those hydrogen potential, sorry, hydro potentials accordingly. We have also the GDP, the gross domestic product. We need to have the population, and those two are very important because we will be using them in case we don't have any geospatial distribution of some input data. So we can at least distribute these according to GDP or population. For example, let's say, I don't know, demands, yeah, for industries and so on. We also get, as Anton already mentioned, we get the load time series, which is actually the demand time series for the country itself in the future. For example, if we say for 2050, we get these demands from so we download them already from Zenodo, where we already collected the demands according to socioeconomic SSP2. We can choose even SPP2 or SPP1 in the future, and then we have them for multiple years. And these are already performed, let's say, estimations of future energy demands per country. And these were based according to population growth, were based according to GDP, were based also according to weather data in the future. So, and these will be used as a load time series for the electricity demand in the future. Anton, please interrupt me if there are any questions to be answered there. If that's already
No questions yet.
okay, so either this is too hard or everything's okay. One of those two. All right, so now after that we move to the rule called build shapes, and this is where actually we build the polygons for each country, depending on the config file. But if you just say you use multiple countries together, um, this way the model will just collect those shapes from the GADM dataset, and then accordingly we'll just calculate or generate the countries, exclusive economic zones, and administrative zones. With these build shapes, we'll see later on what we can do. So there is another rule afterwards, which is the base network. And this is actually where we construct a base power network with buses, transformers, high voltage AC lines, and HVDC links. Here we see already here that those are already shown for the European countries. And these are collected from OpenStreetMaps, filtered, and let's say cured for the input of the model. I've seen also a question before asking, okay, if these if we already do not have enough data or good data for the OpenStreetMaps, the user can always at a later stage also feed in for each bus different inputs, or actually even manually also adapt all those files after being generated, and then the model will not generate these again, and then we'll consider them as input, and then we'll continue according to the adapted, let's say, input data. Afterwards, we build now the bus regions, and this where the bus regions are created according to Voronoi cells. So those Voronoi cells can be based on the electricity network, on the buses, on the demands or generation, but also can be set by the user. Said, okay, I don't want to base them on all of these. I have already predetermined shapes. Let's say the JDM level 1 or any user-defined custom shapes. I want to just do the optimization according to those regions, and the model will use these regions accordingly and will not do, let's say, the Voronoi cells accordingly. Now, we use the Atlight, which is actually also a Python package developed by the PyPSA-Earth community. Sorry, by the PyPSA community. It's actually calculates the renewable power potentials and time series around the globe. So this Python package actually generates, or let's say convert those weather data, let's say wind, solar radiation, temperature, precipitation into energy system data, which is solar photovoltaics, potentials, solar thermal collectors, potentials, wind turbine, let's say wind potentials, hydro runoff reservoirs, COP for heat pumps, and then of course heating and cooling days. This also, as we can see onto the right, for example, here for Germany, so this is what we mentioned before in the morning. Also cut out. The cut out is actually the cut out of the ERA 5 data set, for example, above Germany. So as you can see here, the raster is 30 by 30 kilometers. And we get all the data, we download the data automatically. And these data could be, as we can see here, like wind speed at 100 meters and so on. And these will be already within Atlight, already converted into capacity factors and energy generation accordingly. And these will be definitely clustered according to the previously bus regions defined, either Voronoi or with the GADM or just by custom user definition. So this is how actually those influx, for example, is transformed into those regions. And this is a time series. That's why you can see already the time series for I guess here, I'm not sure, 1 day, what happens with the solar and wind, and all of these are fed into the model. We have from the era already 84 years we can choose from. The default year within PyPSA-Earth is with 2013. Of course, this can be changed accordingly by the user according to the location and to the weather year needed. Also within the acolyte, there is, as we already know, that there is land availability we have to calculate because we cannot use all the full potentials. So we do this within the acolyte model, which takes the input data we downloaded before from the Korean land cover, natural protection areas, Jericho bathymetry data, also height, elevation models, and distance to shores, all of these that are collected, let's say, according to the config file, will be used by the model to just do some exclusion criteria, calculate the area, and then the potential of eligible areas accordingly. Now there is also afterwards the rule-built power plants, and with this we also use a Python package that was also developed by the PyPSA community, which is called power plant matching, which downloads and cure multiple sources of data. For the PyPSA-Earth itself, there are multiple sources, and these sources, let's say the global energy monitoring, open OPSD, GOE, and WRI. In addition to these, the user can also set his own power plants and feed them also in addition to these or in collaboration with these or just by themselves. So this can be all fixed in the config file, and the user can say, I want to use my own, or I want to merge my own with these, or actually just use these only. Yeah, any questions? If not, I'll go further. Then afterwards, we reach the add electricity, and this is where we add all the loads that we already collected, and then the generators also with their location to the base network, where we already formed the electricity network, the base network. And this is where we, as you can see here, we get the bus regions, base network, power plants, and the renewable profiles and hydro profiles. All of them, we can add them to the electricity network, where we have a real full generation and demand electricity network. But from that moment on, we need to actually reduce slightly this network because that has a lot of open ends. And this is where it comes in a later stage, which is called simplified network. But before that, within this add electricity, we also need to have or to fill in the techno-economic data for each and every component. And this is actually what Anton already touched upon in the morning, earlier, where we get and fetch from the technology data, investment costs, variable costs and efficiencies and lifetime for multiple years. These are all already pre-calculated and available on the GitHub repository. As I said, the user can also already put this in a config file as false and then set up his own input and prices and costs accordingly. And that done, we already have built the electricity system model using PyPSA. Now we need to simplify this in order to be solved. Then we need to extend the model to be sector coupled and then solve the model. Now there are two rules. We have the rule simplify network, and then we have the rule the cluster network. With the simplify network, we reduce the complexity of the network by aggregating and removing unnecessary details. For example, links and lines that are dead ends in the network. We also remove some threshold lines that are very low voltage. We do the electrical consistency, so all transmission network will be mapped to the same voltage level. Usually we choose the 380 kV. Then we do also some node clustering for the buses themselves, so transformers and so on that are geographically close to each other, and then we merge them together. And then afterwards, we need to do the real clustering, which is actually matching all of this according to the regions. According to the bus regions, and this is being done by using the k-means clustering technique to partition the network into given numbers of zones, and then reduce the network according to those zones. As I said, this can be also done by setting by the user already that I want to have my own, or according to JDM administrative regions. And then the clustering will not reduce, or let's say it will reduce the network according to those regions and will not do the Voronoi. So now rule prepare network, and this is where we prepare the network for solving. I won't touch upon now the sector coupled rules because there are many additional rules and it gets too complicated and we don't have time for this. Maybe another session for that will do. So for the electricity network, we just prepare the network here based on two wildcards. In the config file, we already previously saw OPTS, which is like some kind of options, and then those two, the second with two wildcard. The first one sets, for example, CO2 emissions, as Anton already mentioned, where reduces the temporal resolution. For example, we also, as we talked about, like the snapshots can be hourly, 3-hourly, daily, and so on. And because all the collected data earlier were all on an hourly basis. And then we also have some additional wildcards for the PyPSA-Earth, which are called SOPTS, but we won't dive into this now. Yeah, and then the other wildcard is actually the limits of the line expansion, so the electricity transmission system. And we have two parts here. We have the first part where we just see, okay, we want to have the volume, limit on the line volume or the line cost. And the second part is if you want to keep it purely optimized according to the cost, or we just put a float number, and with that float number, we just mention, okay, we want to expand, let's say, the volume of the network. We want to expand the volume of the network by 25%, which is 1.25 here. And this is the maximum expansion of the electricity network. Okay, now just to explain slightly the difference when we talk about electricity only and sector coupled. So now we finished the electricity only system, and whenever we talk to sector coupled, we just couple this electricity network to all the other carriers, let's say from heat to gas to through electrolyzers, for example, to hydrogen and so on, many more. And this is what we call now the sector coupled network. As I said, I won't be diving into this 100%. I just want to dive here into something else, which is solving the network. There were multiple questions earlier today saying, okay, can we do long-term modeling? Is it, I'm not sure if already people asked overnight or myopic, so I will explain these here. So the overnight modeling, which is actually taking 1 year in the future and say, okay, I just consider only this year, and which is the final year, and I will model everything according to this year. So all the investments will be according to this year. There's also another way, which is myopic, and we say, okay, we just have or take multiple years in the future, here 2030, 2040, 2050, and accordingly we do a pathway optimization, which is called myopic also. And then we see the influence of, so the optimization will optimize first 2030, and from that we'll take the results, feed them into 2040, and then so on to 2050. And this means that the investments and also end of life of some technologies will also be considered. Another term I want to explain here is also deterministic and stochastic. So there is an optimization which is deterministic, which actually we mostly use, especially in PyPSA-Earth, which is we choose or we optimize to one single result in the future, which is the optimal result of having minimum costs of, let's say, expansion and generation. Whereas for stochastic, for example, we venture into the different possible results in the future and by changing some input parameters. For example, let's say the capacity factor of renewables or might not be exactly as this year we mentioned. It might be changing, I don't know, fluctuating and so on. And according to that, we can just feed into this and do a Monte Carlo analysis and see in the future what are the possibilities if, let's say, the infeed of renewables is fluctuating. So now those are the commands that we can give at the end to solve the network. So if we give solve sector networks, we just solve the sector coupled and an overnight foresight, and the optimization method is deterministic. If we just give the command solve all networks, we go to electricity only network, the same overnight deterministic. And for a myopic, we just say solve sector networks myopic and or solve all networks Monte. And this is called Monte Carlo. That's what we mentioned now, the stochastic um, optimization method. All right. Any questions before we move to some results analysis? I guess it was too much. I'm not sure if everybody could follow up with me. Let's check slightly some questions. Okay. Again, Anton, if you can actually share the link to the collab.
Will do.
All right, thank you. Exactly. To answer your question, Pavan, that yeah, this is possible, of course, to be set as custom demand. It's not, let's say, just purely trivial, just to put as a CSV somewhere, but this is definitely feasible. Just want to say also that the demand we have here for the electricity, mainly we take the capacity factor, or let's say the normalized demand behavior, and then we can also just tweak that, and then accordingly, if you want, let's say, either take another profile or just tweak the same profile and see according to current or future demands of electricity and subsectors accordingly also. All right, so now I will share again Google Colab. I'll just give 1 minute time so that everybody is on track. Here, if I have it open already, I can show also. So for the demand, this is the global demand data for PyPSA-Earth in Zenodo. And as I said here, we can see the SSP 2.6 already for 2030 for different locations that are already prepared that can be downloaded. And this is based on the uh, GEGIS model, which is here, the Global Energy GIS, where they just do the calculations for future projections of electricity demand. This is also, here we get also from the INSD, United Nations Statistics Division. This is where we get all the sector coupled, let's say, demand, current demands. So this is open source. We can download all of these already and then put some growth factors and CAGRs to predict the future. Okay, so I guess everybody's already on track again. Good, so the same, here we'll just go with some few, like really few network analysis, how we can do this. Also with a already model solved for PyPSA-Earth. We cannot really solve the model here because it takes some time, some decent time. But then this is, of course, this is only a small part of what we can do with analysis. There are a lot of already other workshops and other already in the hackathon. We can see here. I can show you also. It should be, oh, wait a bit. No, sorry, PyPSA-Earth. Ah, this should be here. Exactly here in the documentation, we can see already a hackathon that you can actually also start with, training yourself. You also have a lot of other notebooks where you can also just download, learn on how to build shapes, how to explore networks, build the OSM network and plot it and so on, check what is the land availability and all of these kind of stuff. Okay, so now, so we can already install the packages again. We run install the packages. Here in this session, I will use the latest PyPSA just because it has some nice things we can plot with. However, it does not really work on everything, especially because the run, or let's say the network, is already solved in a previous version of PyPSA. So not all commands can be run. So what we'll take is we grab now a PyPSA network for Turkey, which contains the current status and as well as future optimized model for Turkey for the year 2050. Now we download the data. So what do we download here? We download the network, the solved one. We download also the country shapes, so the full country of Turkey, and then we download also the GADM shapes. And here we actually calculated everything according to administrative regions, slightly tweaked, not GADM 100%, because they are around, I guess, 80 nodes. So we just reduced them to 35, I remember. And then we did the calculations accordingly. And here we also fetched the config file in order to read some few things from it. So now we import those, we read those network, GADM shapes, and the config file. And now we can directly just plot simply just GADM shapes dot plot, and then we can see already the GADM shapes. So all those nodes now or regions that we consider for Turkey. If you want to consider one of the regions, here if I just click here, add code, we can see exactly what is this data frame. So it includes some information, JADM ID, geometry, GDP population already, and so on. So if I want to just use, let's say, TR 4.1, or let's say here I chose TR 11.1, and I run it, and this way we can just, you see only one of those regions. Another way also to view everything in an interactive way, we just plot JADM shapes.explore, and we can see interactively the map of those JIDM, and then also see all the data is inside. So we can see directly population, GDP, and so on. Or we can even use also HVplot, which is a powerful and interactive panda like with the plot API. So we just, instead of plot, we just put HVplot, and then accordingly we can see something interactive. Here we just say or tell the plot that I want to have, when I hover above it, I want to have the JADM ID, the population, and GDP only. And please also give me the colors according to population. And with that, we can see already here. So the scale here is according to population. And once we hover, we can see already population, JADM ID, and GDP. Anton, if there are any questions, please interrupt me so we can answer them also right away. If there are no questions, we can just move on and then also inspect the data inside the network. So as we already saw before with the Priyesh, for example, we can just check the network itself and say, okay, how many nodes inside, how many snapshots are we having, what are the storages, what are the generators, how many of them, just to see, okay, what kind of network do we have. So a small description of the network. We have bus, 738 buses. We have 37 carriers, 540 generators. Yeah. So the snapshots here, we see this 2920, which is not a full year. It's actually an aggregated or weighted snapshot. So I guess it was here 3 hours, 3-hourly. Once we run now to check the length of the buses and locations, this means we want to check again how many regions we have. So we have 37 regions. And here we can just check slightly directly that, okay, let's get the buses. And here head, it means only gives us only the first 5. So those are the buses with the names according to each region, the location also, and all the remaining attributes. We can do the same for the generators. You also see here geothermal, CCGT. So we have the also Pinom min, Pinom max, pset, and all the other already previously fed in data and at the same time optimized data. The same here goes for if you want to have the time series. So we just put, instead of generators, we put generators T, and then from that we go to the Pmax PU because there are multiple other stuff to see there. So the Pmax PU is the capacity factor of those generators, and we only just see some few of them. Here we see CSP, off-wind 2. Here we see 2 because we already considered 2 levels or 2 types of offshore wind and onshore wind at the same time, each having different capacities and profiles for the same region. Similarly, we now can visualize already the first month of generation time aggregated by carrier here. So as we can see here, for example, this is the carrier, CSP, off-wind, and so on for each and every region or node. So what we do here is that we group them according to the carrier itself. So all the nodes are grouped together, and then we sum it, and then we show only the first months. So plotting this gives us already the different carriers for the first month at a time series. Now here we can also extract some part of these. For example, here we can extract solar and wind, and then we plot them. The things that here for example, I just got only the first part because here there's a lot of, as I said, there are already 37 nodes for each solar. So if I just remove this one here, if I remove this here, and then run it again, and then we will see the full months, which we barely can see anything inside. So this is all the onshore winds for all the different, for each and every region. So we have different profiles for solar and wind for each and every region. As Priyash already said, we have the statistics module, which is a very, very handy thing to just analyze results once we have a network. So it can already tell us a lot. It can already tell us about the generation mix by technology, installed capacities, line loading, cost and revenues, CO2 emissions, regional balances between the regions and power flows. And this actually is very handy in order not to write everything from scratch. For example, we just say here, S is, let's say, network.statistics, and I want to see, okay, what kind of statistics I have there. So if we have for generators, for stores, for each and every component, we have the different carriers, and then we have the optimal capacity, installed capacity, supply and withdrawal, which is the energy flow, the energy balance itself, and of course, many other stuff, let's say CAPEX, OPEX, and so on. And also curtailment. So let's say now we want to check only the generators. So we want to take the generators part here. We just say S comp, which is the components. If I just check for generators, we get generators. Now you guys, you can also do for other components. So just check for store or load. Okay, if we want to now have, let's say, the optimal generators capacities, and we can take that right away. There's also S optimal capacity. So we just get the optimal capacity now and not, let's say, supply or something else. So we just get the optimal capacity. And from that, we say, I want to have only for AC and low voltage. So I don't want to check any other carriers. And I want to have mainly the generators. So according to that, I can divide by 1E3 or 1000 to get to move from megawatt hours, sorry, from megawatt to gigawatt. So everything within the network is either megawatt or megawatt hours. This you can actually read also in the on the PyPSA-Earth already documentation. So what we see here is already the capacities for each and every carrier in already terawatt hours. But now we want to actually visualize some of these things. So also PyPSA has a plot function or plot module that provides a small set of standard plotting functions. Those are very quick, also quickly visualizing stuff. Let's say network topology, line loading and power flows, generation dispatch over time, and so on. And here we just use again the back end that is not that is actually Plotly, which looks nice somehow. And we just say from the statistics, we want to have the optimal capacity for generators and then sort the values ascending. So only according to from large generation to small generations. And then please plot them as bar. And just by running this, we already get an interactive one where we just see also the optimal capacities. So for Turkey 2050, there's a huge potential of solar. There is also a small expansion of geothermal, for example. Yeah, and very large reductions also for lignite and gas. Please interrupt me if you have any questions already. So also for the statistics, we can just also check the capacity factors. So if you just run s.capacity factors or network.statistics.capacity factors, we get also the capacity factors for each and every carrier and component. Similarly, we can also get the energy balance. And for that, we get it also by bus carrier and carrier. So here all on the AC bus, which are the biomass, coal generators, and so on. And then we have the other buses where we put here, for example, water tanks, heating, and so on, and solid biomass. Now, after checking slightly what is there inside our network NC file, it has a lot of data. All these data are stored in arrays above each other. So we can access them, as you can see, very easily. And from the statistics already module, we can actually directly visualize efficiently and very fast after already running the model. So now let's explore slightly the demand. So if you just click on network.load.head, we just see already the loads per carrier with its P set. So it's nominal power. And if you want to plot, let's say the energy balance only for loads, and we want to have the sum of them on all nodes, and then plot them without specifying if I want to have only the AC bus nodes or something like this. So here we get all the load, which is either also coming with emissions. So emissions, here we see them as positive, and all the other loads are negative. So we have the demand of industrial electricity. Here AC is mainly the residential demand. We have urban central heat also as demand. It's not AC here, so we did not really specify that we want to have only the electricity connected loads. This can be easily changed by just saying I want to have only the bus carrier of AC, for example, and then accordingly the plot will change. Okay, we did not have low voltage back then. So now we only have the AC connected load. So now let's move to the transport sector itself. If you want to check, for example, the demand of electric vehicles, internal combustion engines, and fuel cells, we just, again, go to the statistics, we go to the energy balance, we go to the loads, and then we say after that, I want to have only the carriers that contain land transport oil, fuel cell, and EV. And by running that, we already have the data or the load for those carriers. And we can see already the bus carrier here. So we have here for fuel cells, hydrogen, for oil transport oil, and for electric vehicles is lithium ion batteries. So we can plug this divided by 1E6 to get that in terawatt. And we have the land transport, electric vehicles, land transport oil, and then the land transport fuel cells. This is, of course, all those demands are, let's say, set according to a scenario in the future where we say, okay, we'll be having a large share of electric vehicles in the future, reduce the oil transport demand, and then have a small share of fuel cells. All of these can be already set by the user itself in the config file. Any questions? Just do you need a pause of 5 to 10 minutes, maybe a bio break or something? Then we can continue afterwards. What do you suggest? Okay. All right. Let's have maybe 10 minutes bio break. So we start again at 24. I hope everyone got back and got the chance to refresh themselves. Okay, let's continue. So we were exploring the generation side still, sorry, the demand side, and now we wanted to check slightly like the heating system or the heating sector. And we seen slightly, let's say at the beginning, the heating subsectors for the AC or for the connected to the electricity. And now we can actually also have the heating energy supplied by heat pumps, district heating, resistive heaters, and gas boilers. How is this actually distributed per shares? So what we do is, again, we call the network.statistics, and we say supply, which is the energy supplied. Then we say we want to have the components link because most of these are, as actually all of them are links. So those are converted energy coming from, let's say, either here from boilers, electricity, oil, or so on. So that's why we just put the components as links. And then there is another option we can say if we aggregate the time. So before, if we want to have time series, we say aggregate time false. But now here we want to have to sum actually. So we want to have the sum of over all the year. And we want to have only the carriers that have heat, boiler, pump, and CHP in their carrier name. Yeah, and accordingly, so what we have here, we get the heat supply stats. If I just plot it here, or let's say not plot it, show it here. So what do we get here? As you can see, we have a lot of carriers that are residential rural gas, boiler, residential rural ground, heat pump. So we have a lot of rural and central, or let's say urban. So we differ between rural and urban according to GDP and also according to population. And now, in order not to show all of these, we need to aggregate them according to the carrier. Let's say we just put gas boilers, heat pumps, resistive heaters, or combined heat and power. So that's what we do here, and we plot it. We get that in the future for Turkey, a lot of combined heat and power is possible for the heat supply. Um, yeah, as well as gas boilers, then around 10% or 9.5% heat pumps, and the rest is resistive electricity heaters. So that's a very ambitious, of course, scenario in the future where we have combined heat and power, but they have the potential for it, and this is possible. Now, if we want to explore slightly the generation side, so we can still always call network, but then here, just for simplification, I just change it. You can call the variable n. So we copy the n, and then here we map the colors and nice names for plotting. So this is something, a small script I wrote where we just put some nice names and colors for our plotting. So nothing really sorceress. And from that, we can plot here the map of the current energy system. So here we just do it the same old-fashioned way somehow by just going from the network, go to the generators, say I want to have the load there, and please group by the bus and carrier. And then I want to have the pnom, which is the capacity. For generators, the same thing I will do for storages. I get also the pnom for storages. Then I concatenate, or let's say I join them together, and then also plot accordingly the links between the nodes, and then specify also the links widths according to the pnom of the lines, and then put some legends. So we can see here the current situation for the nodes of the generation fleet, let's say. We see a lot of coal, then afterwards lignite, and then of course combined cycle gas. Whereas on the right, or let's say in the east, we see a lot of runoff rivers and reservoirs. And then in the south, we see also a nuclear that is actually starting soon, hopefully. What was considered is that actually it's what I considered there by collecting the power plant matching is that by collecting saying that also that under construction is considered to be already installed. This you can by the users themselves just say, okay, everything is under construction. I don't want to have it for the current time being, and then just go for the only existing. All right, and if we want to map the future, so we do something very similar, but instead of pnom, we just go for pnom opt, which is the optimized, and we run the same thing, and then we see the optimized system in 2050 looks totally different, where there's a lot of solar power available, very slightly amount of wind, because already the amount of solar potential is huge. We see still around the area of a large demand, which is around the capital, not the capital, sorry. So we see a lot of oil, we see a lot of gas there still available, and lignite to just accommodate for all the fluctuation and so on for the demand. And then also we see some lines that are expanded at the same time. So now let's plot the capacity expansion itself only. So how much was expanded between all the generators. Now we can switch back to the statistics because this does it very well. And then we just go for the optimal capacity and say generators, and then we get it in gigawatts. So the largest amount of expansion is solar, then followed by geothermal. So if you want to go further here and say, okay, what are the share of different carriers by capacity? So we also go now to the installed capacities for generators. And here we just also mention that we want to have the storage unit, where actually the reservoirs and dams are considered as storage unit. Before Priyesh today said that that these are considered as storage units because they have inflow and then they generate accordingly. Yeah, they generate accordingly the electricity. So after doing all of these, we just say I want to have by carrier, and we just use also another way of plotting here, showing also interactive plot of coal having the largest capacity in the country, followed by lignite, and then combined cycle gas, and then reservoirs and dams, as we already saw on the map. So, but what are the shares of those capacities while generating itself? So while generating, here we just want to go now to the energy balance generators and then get the generation. So we see that per carrier, we see that the solar generates the largest amounts, and then followed by lignite, and then geothermal, then reservoirs and dams. And this is for for the future. So now that is done, we can also switch now to explore some energy balances. So we want to see what are the supply and demand on a, let's say, time series and static way. So what we do here, we just first go to the static way and then also go to statistics, energy balance. From that, I want to have only the AC, so the electricity system, and please group by carrier, sum them, because I don't want to have a time series, and then divide by 1e6. That gives us, converts from megawatt hours to terawatt hours. Then put it as a data frame, transpose it, and then rename the columns according to those what I give. And then accordingly, we can plot already the energy balance, the total energy balance for the whole year. So we can see already it's an interactive also plot where we can see already how much terawatt hours have been generated. So everything that is positive has been supplied or generated, and everything that's negative is demand. So we see here already in Turkey that there's a huge amount of the industry demand for electricity, and then followed by services electricity. So the same thing can be done also now with a time series. So what we do is we just add here group by time false, and accordingly we get the time series, or we keep the time series. So once we do it, then we just also say, because actually the time series is very large, and if we plot it now, we will be barely able to see anything. So I just take only a slice of it, of around 300 snapshots, and then we can plot it again. So this is here also an interactive plot where we can see already for each and every times snapshot, we can see all the generation and demand for different technologies and carriers. So this is for Jan. We can see here at the beginning, also we see a lot of combined cycle gas because of solar being very low. So it kicks in. At the beginning here, we see slightly some amount of onshore wind also being used, whereas here a large amount of lignite kicks in to also balance the system. Any questions? All right, I can see that most of them being answered. Nice. All right, let's continue to explore some few networks. So we have multiple networks. I won't explore all of them. So mostly the electricity network. So what we do here also network.links.head. So this is not the electricity now. We just see all the links where we can see also some connections here. Links are, as described before, they are connected in two buses. They can be uniflow or multi-directional. So here we have, for example, an example from CO2 store to the atmosphere. So this is a link between the CO2 nodes and the atmosphere. And on these CO2 nodes, we have, let's say, multiple things connected to it. From one of them is called the CO2 vent. We have also sequestration, for example, underground. We have industries that use also CO2 are connected to this. So if you want to check the transmission lines, we can already get the X and Y from the buses, then get the network.lines, and then plot only the SNOM opt, which is the optimized lines. And then we specify the line width to be actually the opt, so SNOM opt over 1E3 to just get it in gigawatt. And here we can see already the optimized transmission lines between the nodes. This is of course, it's not only the expanded, it's the optimized itself. So it's including also the existing. We can definitely do the same by subtracting the opt from the nom itself and then plotting, and then we can just get only the expanded ones. Similarly, we can do something similar for the hydrogen pipeline. So the hydrogen pipelines are also links. So we do the same for the hydrogen, and then we can get already, because hydrogen does not exist already previously, we can see here only the expansion of the hydrogen network. And as you can see, the largest expansion here in the south, because actually the scenario back then considered there is actually some export from different ports for hydrogen. And one of those ports is in the south, and because of there's a lot of huge potential of solar, we'll see later, and wind in the south. and east. That's why the most export is being done in the south, and that's why the reinforcement um, of electricity and as well as the largest expansion of hydrogens are being done in the south. And here we can see that the optimized hydrogen pipelines are in gigawatt kilometers because because the expansion can only be based on capacities. So we can go further now and see now the potentials that we just talked about and see, okay, how does it look actually for each and every state? Here we can run our map, actually the PV and wind potentials. So for the PV, we just get those potentials also from, if I open this again, we can actually get those potentials, as you can see already, from endo generators, and then we go to and then we just get it from the Pinom max over the area. So we get the area of each and every region, and then we get the Pinom max over this area. That's why the Pinom max is already fed into the model or calculated already by Atlight. So this is the maximum potential that can be reached by each state. And here also in interactive, we can see already that here for the solar, the south as well as the east has a huge potentials for Turkey. Even though the demand is not in that location, the demands are mainly in Istanbul and Ankara, and then here also in the south. And that's why we can see already some expansion of pipelines and electricity network in order to get this cheap renewable energy sources delivered for export. And for export of hydrogen, and then also to satisfy the demand. The same thing can be done also for onshore wind. And here also we see the maximum potential. We can see also this somehow the same, or not the same, but very similar locations have the same, has also large potentials per kilowatt square. As I already said before, analysis can be done indefinitely almost, of course. This is based also on the research question, what do we want actually to answer with our modeling? Back then we were focusing only on the export of hydrogen potentials and how and where the export was going to be coming from which port, what kind of expansion, infrastructure-wise, and generation fleets. And that was done, of course, after satisfying the future energy demand within the country by itself. So we can also, for example, also here show and map the electrolyzers, for example, expansion, and even have the time series of the electrolyzers and so on. But this I will leave to you. You have already the network. You can play with this as much as you want. And then, of course, we stay there for any questions in the future. You can contact us. As already mentioned before, we can go to Discord. You can join in Discord, have discussions there, ask questions, attend the meetings, understand what's happening, and so on. I also have a small list here of the documentation, as I showed before, where you can already familiarize yourself with a lot of steps that we did not cover today. In addition to that, there is also a lot of workshops and similar notebooks already by OET already being done, also by the Technical University of Berlin, TU Berlin. And of course, the videos from Anton that are super helpful, especially for installing the model and making it run at the beginning on a local machine, and of course, of doing some additional analysis. If you want, I don't have any time anymore. We just need to open some few questions, unless you want to dive slightly into one of the rules that I did not cover, which is, I guess you can do this by yourself. I'm open to questions. Are there any questions, Anton, that we did not answer yet?
I'm not quite sure because at some point I didn't manage to see all of them. If I already answered all of them. But if not, just yeah, raise your hand again or yeah, ask it once again. Then
I
I
mean,
will
I
try
see.
to
I
answer
see
it.
the last question now from Mohammed that he's asking also green steel share supported in PyPSA-Earth like PyPSA-Europe. This is not yet integrated. No, we don't have the different, let's say, industries. Let's say steel and so on, are not represented. Only the demands mainly are distributed here within PyPSA-Earth according to the carrier itself, and not according to the technology. This can be done. Um, if you are working on this can be helpful also for everybody if you can just already start coordinating with us. We can integrate this to the model and make it available also for everybody. And of course, get help into implementing this. Yes, of course. The slides will be provided to you. And then, of course, the links are there where you can actually also um, download again, play with those notebooks. Yes, the question from Pavan, how can I add an additional constraint as part of the model? The constraints can be added on multiple locations, but mainly we can also add them if there's like in the prepare network and serve network, actually. We can add a lot of constraints there. Before solving. So after building the full model, everything, you can already put some constraints there on whatever was built before solving by itself. Okay, any other questions? Okay, power to X, the question, what about power to X except hydrogen? So we have also in the model um, some integrated power to X exports that are not till now merged with the main. So we already worked on this. We already have power to X export at least for three. So ammonia is included, methanol, and hydrogen, with also the shipping calculations and the shipping fleet and so on until the import location. This is already done. It's not joined, merged yet with the main repository, but if you need this something very urgent, we can actually also talk about this. We also have something in the pipeline by preparing also desalination with Anton. So he's working also on desalination to add to the model desalination, because for the current or for the time being, the user has to set for each and every region the water costs. But in the future, this will be all built in within the model, within the workflow. Okay, we have one question asking, okay, to be interesting to have tutorials and best practices how to make manual adjustments. Yeah, I don't think this is already available, right, Anton? So this would be something interesting to be tackled.
Exactly. There is no real tutorial or something like that already available. I would suggest to just fork PyPSA-Earth. Um, if you can sort of yeah, yeah, if you can sort of implement your changes to it, implement it, adding your own customization to the model, and after yeah, validating your results, just open a PR. I'm sure your customizations are very much useful for the whole community. So it's then always good to share your new implemented features with the whole open source community. And then most of the time it gets integrated into, yeah, into the current main. And then all the others can also profit from your cool new features and customizations.
Exactly. So the more the merrier, the more people work on this. Of course, everybody, that's the beauty actually of open source. You don't have to do everything by yourself. Everybody builds on the work of previous people. And then we get all a better, let's say, results or modeling. Okay, let's see more questions. For ancillary market, is it helpful? I don't think so that this model is suitable for ancillary markets. I'm not sure if actually this can be done, but not actually with PyPSA-Earth as it is now. Okay, we have one questions from Pavan again. In India, when I was working on weather years, 2013 was used. Can I change 2019? Yes, of course. You can set, as I said, we'll have already 84 years provided by ERA 5. So we provided 2013 because we already have it also on our drive somewhere where you can download it right away. But you can get any other year also directly by downloading those data from the ERA 5. You just have to set up this. Actually, Anton has a nice video for this where you can set it up and then directly download from there all the data for this year and then do the run accordingly. Okay. Is there an example case for hourly dispatch analysis? I don't think there's a notebook that has been done for that exactly. I personally haven't worked on hourly dispatch, like dispatch models. I more work on the capacity expansion and so on, but this is definitely feasible. Maybe you can find something in PyPSA Europe. I'm not sure if there is any notebook available there. If not, you can join us, try to run it. We can help also with this, and then this is definitely feasible. It's actually one of the features that PyPSA-Earth can do. There's also one feature where you just run the model, optimize it, and then after running the model, you can just do only dispatch according to the optimized model. So this is also feasible. So there is one question here, last questions. So PyPSA is a long-term planning model tool, best for 1 year optimization, right? I mean, we answered this. This can be 1 year optimization, whereas you can also have a myopic, so multiple years connected to each other by feeding in the results of each year into the input of the following year. So this is the myopic already solution. Yes, a nice question also. So there was a recently paper with PyPSA Korea. How does regional models differ from the PyPSA Earth? So the PyPSA Earth is actually mainly, let's say, the mother model that can actually model any country in the world. However, of course, people fork from this model, that's PyPSA Korea, and then change a lot of the scripts, maybe add some new scripts, or even change the input data that are super tailored for Korea, and so on. And that's how a model becomes uh, purely tailored for this country. But as a start, they all start from PyPSA Earth. Um, Nice question also. Do all functionalities of PyPSA Europe exist in PyPSA Earth? Um, not all functionalities in PyPSA Europe are existing in PyPSA Earth. PyPSA Europe has a lot of different, let's say, types of functionalities because first PyPSA Earth started before PyPSA Europe, and a lot of input data are different, a lot of research questions are different that are not available on PyPSA Earth because are not needed. So a lot of functionalities and technologies that most probably will not be implemented, especially, I mean, we already implement PyPSA Earth mainly in countries that are not super advanced, for example. However, these functionalities can be easily adapted from PyPSA Europe into PyPSA Earth if there is any need for these. But in general, those two models are very close, however, yet different in many ways from some functionalities in addition to data input. So a lot of data that are available on the European level are very highly tailored purely only for Europe, the geographic area, whereas for PyPSA Earth, we need to search for global data sets. And that's why, for example, it jumps into the previous question where PyPSA Korea becomes a different fork where they find their own data sets where they tweak the model slightly to just have better results for their model themselves. So for market modeling, 15 minutes price. Yeah, for the nice question also. So market modeling, so how 15 minutes price is in operation? What is the potential of PyPSA to be utilized on this area? PyPSA Earth itself, PyPSA Europe also can slightly be used for market modeling, but it doesn't really, um, let's say it does a full optimization with the least cost. So it doesn't really give the insights of the different market players, of the different, let's say, reality of a market modeling. That's why we have already some studies that has combined agent-based modeling for the market itself, and then feeding those results to optimization model of PyPSA, where it optimizes all the generation demand and expansions accordingly and curtailment and so on, and then fed back into the agent-based model of an energy market itself. It gives the best then combination. Okay, it's myopic modeling. So it's myopic method of modeling. If you go back to the slides, once we share them, you can see already the difference between the overnight modeling, where it's just only 1 year, all the investments are being done, or myopic by feeding year after year, or let's say chunk of years together as a myopic simulation, or let's say optimization. Yes, thank you, Anton. I don't know anything about Mosaic solver.
Me neither.
Yeah, so most probably not. And if it's important for you, we can also discuss this, but I personally do not know anything about it, if it's open source or not.
All right. Then, do we have other questions? If not, thank you very much for your participation. Feel free to join our weekly meetings on Thursday. It's always on Thursday, 10 a.m. Or 9 a.m. GMT or 4 p.m. GMT, depending what suits better. And yeah, if you have any questions or if you want to work on something or something like that, feel free to reach out. You can contact me or Eddie. I guess we will also share our contact details afterwards with the slides. Exactly. Thank you very much for the participation. I don't know, see you. Do you want to close it or?
Yeah, exactly.